Okay, so our project is focusing on doing malaria detection, and so we are working with biomedical cell images, and the focus is around detecting the malaria at early stages, and also performing it on a special type of microscopes, which are what we call low cost. So we'll go back into it. It's the review for presentation. So to kind of give you a background about what is malaria, every year it's about 200 million cases with 400,000 deaths. So it's something that's very, very important in the medical field. We have those, you can usually see them through using microscopes, and you can see them cell by cell. And then, there's the 4 stages that we are able to see here. So that's the kind of, we're not just detecting malaria, we're detecting what stages are we seeing on each cell if we're detecting anything. So, which is what we can see here. So the idea is there's 2 types of machines, 2 types of microscopes that are available in the field. And so the first one, which is the high cost machine, is a bit better looking. So when we want to do so here we have a better looking. So if we're looking to annotate data, we're gonna use those machines because it's gonna be much easier for someone to kind of draw on it or kind of see if they're seeing any malaria or anything. But the problem is they don't really have those nice microscopes in most public health centers. So if we want to do an algorithm that's going to be useful, we wanted to apply to low-cost microscopes. So that's where the idea is to train a data set on those high-cost machines where it's easy to make annotations and labels, and then have the model be performance and testing it on low-cost microscopes, which is what we're seeing here.
So we are like dealing with the problem of domain adaptation from high cost machine to low cost machine in testing. First we looked into the prior work. So this is a brief a schematic diagram of prior work. So it is from the same lab alumni like Waqas Sultani. They use like a 2-stage detector, so that is like region proposal based detector like FASTA RCNN, and they were basically trying to first adapt the domain using the fake fake stylized GAN kind of images, so from this HCM image they first generate the fake low cost images, and they try to improve the accuracy, like adapt the domain like that. So problem is that like they require like multi-step training. First they train, generate the GAN images and they train GAN for that. And after generating the GAN, they require this kind of fine-tuning. Fine-tuning process. So from the corresponding images of LCM and HCM, they take it as a positive in the triplet loss. We can see like matching corresponding images are the positive, and the other field image it's taken as negative. But major limitation is that like their improvement was because of the very weak baseline. So that's what we feel. And so we try looking into some research questions like can data augmentations like be used like effectively to adapt the domain from HCM to LCM. So it could be like very simple yet effective solution. Another thing is like instead of this multi-step training, can we have like something end-to-end framework? So end-to-end framework, and we also try focusing on the single stage detector, because in two stage detector, like if there will be some changes in the prior backbone, it will be propagated through the second part of the network as well. So that was our hypothesis, that like we'll try to solve it using single stage detector. So yeah, and right choices of like detection losses. Yeah, so our method is very simple. Like we use single state detector YOLO based. So YOLO framework is basically made up of like a backbone architecture, which is like CSP darknet. And we use it as a feature extractor and like because it's very computationally friendly. And so second good thing about that is it has a path aggregation network. So like it tries to, it aggregate the features from various hierarchy of the model. So it doesn't, yeah, that's why it very effectively, able to detect very small objects as well. And yeah, and the third part of the model is that detection head and non-maximum suppression. So yeah, so this is very standard pipeline people have been using. And so we are actually using YOLO V8 implementation of that. So which reduces, like prediction boxes, like because it's anchor-free approach. And that's why, this non-maximum suppression, like it takes very less computation like over the standard YOLO. So it reduces computation a lot. And yeah, here is a schematic diagram of YOLO. Like it first, like, aggregate the feature here, like from various hierarchy of layers and tries to, detect, on these aggregated features, it tries to detect the objects. Yeah, so dataset we are dealing with is M5 dataset. So which is called like multi-microscope, multi-magnification malaria dataset, which is proposed in the same paper. And it is the largest dataset available currently. And we can see the scale difference, like it has like 20,000 cells annotated, like compared to prior works. And it has 3 scales, like for example, like if we look at, scales is defined as at like, field of view. So 1000x, 400x, which is like zoom version, we can say. Less zoom out version, yeah, 100x. And 2 types of microscope, that is like low cost and high cost. So performance measurements, we are considering very standard metrics, like following the prior protocols, which is precision, which is like fraction of true positive among the predicted labels. Recall, amount of like, parasites we are trying to retrieve from the total number of parasites. And MAP, like, so MAP, it's the, we believe it's the more reliable, and like that's also, supported by that paper. So yeah, so comparison with the prior work. So it's, we see like the huge improvement over state of the art. So compared to prior works, like we followed the exact same protocol, exact same resolution. And so our assumption was true that like the prior works, they had like very poor baselines, and that's why like they were looking state of the art. So our improvement is like 72% in this protocol, like where source is HCM and test is LCM. On 1000x scale, we are getting like 72% improvement from prior work. On the 400x, we are getting like around 20% improvement. And these results are on MAP at the 0.5 IU threshold. So that's very, very strict metric, we can say, like 0.5 IU threshold. And we have like 86% less parameters compared to prior work. So we are using only 3 million parameters, whereas prior work had like 23 million parameters. And our method is end-to-end compared to like prior work, like which require like fake image generation, pre-training, and fine-tuning multiple stages. So yeah, about ablation. So with the default YOLO augmentations, we were getting like 41. And with the carefully done augmentation, we were getting like we get like 2.2%, 5.2% improvement. So our augmentation selection was mainly because of like the color jittering, as we seen like from here. From high cost machine to low cost machine. Actually, I'll cover that in the result section. Yeah, it was because of color jittering and scaling, because like the low cost machine, it has like slightly different field of view. So random scaling, it has like, very significant role. And so we also, did ablation with like various pre-training from scratch and from MS Coco. So from so prior work had access to like more pre-training like compared to ours. So they use like cycle GAN weights, ImageNet plus Coco. So whereas we only use MS Coco, and even our scratch results like 43, they are better, 15% better than the state of the art. So yeah, about qualitative, yeah, maybe Tristan.
So for this is just images that we're able to see. So if you first take a look at the images, we can see here that most of the, here we're actually looking at trophozoites, which is like the third stage of malaria. And we said that we're detecting, here there's 5, we're detecting all of them plus 1 false positive. So those are, of course, really good results. So this image itself is a 400 times zoom. We're having a mean AP of 40%, which is, as we discussed, really good and state of the art. We're having a better time with precisions, which means that if you look at here, it means that if I recall it right, of all the what we're detecting, 78% of them are correct, are actually, and then we have poorer score for recalls, which means we're actually missing a few trophozoites, which is not the case that we're seeing here. And then on 1000 zoom, we actually have even way better results, which means, the importance, because, of course, we see more details. And so the results here are even more impressive, especially recall, which takes a huge boost from the 400 times zoom. When it comes to each class, so we have those 4 classes that we talked about, with the most common one being ring, which we can see here, the detection is almost the average for all classes. There's 2 classes that we do a really good job at detecting, which is gametocytes and trophozoites that we're seeing here. So the precision and recall are very good. And then there's 1 class that we struggle with, which is schizoids. And then that class is where it's very likely due to a class imbalance, where there's not that many of them in training. So when it sees malaria in a cell, and it's, schizoids, it's probably gonna detect, call another class, just because that's more likely. So we do have poor results with schizoids, so that would need maybe more mutation for that specific class. But that's the point of this, and that's what we're noticing. For the conclusion, well, first of all, we developed a framework that works for those low cost and the microscopes, and that's really good to see. The baseline is really strong. Just making this YOLO V8 worked right away, very good results. So that kind of shows like how important the baseline model is into selecting the right model. And then the state of the art results, the good mutation, all that is leading to good results. So we're seeing something very good. And then we're gonna make the code publicly available so that it's easy to use for everyone. I'll pass it over to Ishan again.
Yeah, so and like for the next steps, like we will try to improve like results further, like with the comparable number of parameters, like we still have room to like increase the model capacity, and we'll try to like study how it generalizes to like with different backbones, and we will have like a detailed ablation study on like the augmentation strategy, because we played with like many other things, like for example, like the color jittering and scaling for field of view. So yes, so that's the plan for next.